Good day, everyone, and welcome to the Global SMT and Packaging panel discussion on thermal management in confined spaces. The clever ones amongst you will have noticed that I'm not actually Trevor Galbraith. I'm Keith Bryant, standing in for him today, so hopefully I'll do a good enough job. Anyway, welcome everyone. We have two really good panelists today. Chris Hanson from Ventec. Maybe you'd like just to say a few words quickly about Ventec, Chris?
Yeah, absolutely. So I manage for Ventec the insulated metal substrate business unit. Ventec is a company that focuses strictly on PCB laminates used in a multitude of applications. My business unit focuses on thermal. We have a business unit that focuses on polyimide laminates used in aerospace and military applications. And then we have a signal integrity business unit that focuses on high-speed, low-loss applications. I've been in the industry, the thermal industry, for just a little bit over 30 years, 4.5 years with Ventec, and then before that I was primarily with a company called Berquist that made both insulated metal substrates used in PCB applications and also thermal interface materials. So thanks for having me.
No problem at all. As I said, ladies and gentlemen, yeah, we do have a pair of experts with us. Richard Boyle is probably known to many of you for his travels and presentations around the world for many years, but his company has changed recently, so maybe you'd like to add that in for us to start, Richard.
It has indeed, yes. I was going to mention that. So until June of this year, I was part of the Henkel Corporation, looking after the materials on printed circuit boards, so consumables, that kind of thing. And a big part of that was the thermal products. As of June, Henkel divested the solder business to Harima Chemicals of Japan, and I've transferred over to Harima as part of that divestment. So my main focus at the moment is back with all of the solder materials, which I've been looking after for 37 years, but I've still got up-to-date knowledge as of the 1st of June of all of the materials that Henkel had in their portfolio. So really covering all of the consumable side of it to marry up with Chris's side for the laminates and the PCB.
So, right, we have the perfect pair. I'm going to start with a question to both of you. We're all sort of in the industry as kind of consultants to an extent, and we do get occasionally called in to see things that have gone wrong. So in terms of thermal management, what's the worst thing that you've seen so far? And I'll start with Richard.
Components exploding, PCBs delamination, catastrophic failures in products. They're pretty much some of the worst things I've seen.
Yeah, that's good enough. Can you top that, Chris?
I really can't. I would second the words of Richard 100%. I've been in labs to see boards that have LED boards used to light bridges in Los Angeles that were completely melted. The boards are FR4 in nature or structure, and the LEDs were driven so hard that and there was no convection cooling of any sort other than a little breeze on a cool day, which doesn't happen often in that region of the world. But the LEDs actually melted the FR4 boards to a level that the boards outgassed, and the outgassing then covered all the lenses of the LEDs, so the light output virtually became zero.
And I bet that's when they actually found that it was going wrong.
Exactly, right. Yeah, exactly. So effectively, the boards functioned at the time that the issue was realized, but catastrophic failure. And to be honest, I think Richard would agree that the first place customers see this is when they submit, at least in my experience, when they submit a product to UL. And oftentimes they run the gamut of a design and what they might want to use, and designers, engineers might want to take a year to design a product. Well, they're given a month, so they hurry through a product, submit it to UL, and they spend the $10,000 to get the recognition certification, only to get a statement in 2 weeks that your board's failed because they overheated. So
yeah, I mean, you're right. I mean, it's very few companies. Some companies do factor in the thermal consequences of what they're doing, and they try and mitigate that with looking at what they can do to transfer that heat away. But you're right. Unfortunately, a lot of companies only actually look at the thermal side of it when they've seen an issue, and
exactly,
that's a very costly way of actually doing it.
true statement.
Yeah, well, my next question was going to be, and what can be done to solve this? But I guess at the stage that you're talking about, basically this catastrophic failures, there isn't much you can do apart from
Panic
try
really.
quite a lot.
Yeah, buy lots
yeah.
of stuff and panic. I mean, there is obviously, there's lots of stuff you can do at the very beginning when you're looking at the power consumption, when you're looking at what you're actually trying to do, when you're looking at, if you're doing lighting, if you're doing high power, control boards or something, it's going to generate heat. So you can factor in where those hot spots are going to be, and you can try and design in something in the way of heat shields or something in the PCB, or add chemicals. But as I was saying, very few companies do that. More and more are, but it's not as good as it could be.
So you are actually seeing more designers get involved in thermal management now then, because I know a while ago it was almost like separate processes, design the board, build the board, assemble the board, put it into a box and get it to do something.
Yeah, I've got to take my hat off to the automotive industry. They're the ones that are really ramping up that part of it, looking at the thermal issues that are going on, and they're looking at it all over the car. So they're looking at it for the battery packs, they're looking at it for the control boards, but also obviously people like defense and aerospace have been doing that for a long while. It's really going to be the infrastructure people, the telecoms base stations, those types of industries that are going to probably need to catch up a little bit.
And Chris, are you seeing a more joined up approach going forwards? I know Ventec have what looks like a really beautiful ebook about design for thermal management. Are you seeing a good take up from designers for this?
Excellent question. And believe it or not, that ebook that we wrote a few years ago, we just finished and released a second version of it. That still today generates probably on the order of 20 to 50 leads a month. So, and whether or not for me those leads become a piece of business isn't really maybe the great story here. What's great here is that companies, designers, engineers, research and development groups are taking a more proactive approach to thermal, as Richard mentioned, versus having it be a Band-Aid fix later after there's an issue at UL or in a burn-in cycle. So it's great to see the engineering community jump on the topic of thermal. Everything's getting smaller, right? That maybe show my age a little bit, but 20 years ago, a full brick DC-DC converter was sold at 50-watt characterization, and today you can get that same device in about 1/4 the size for the same wattage. And reducing products like that without any convection or any liquid cooling just creates a ton of waste heat. And the same in the LED world. They used to use hundreds of LEDs on large boards. Now the boards get smaller. So you look at a headlamp design, for example, the board is small and there's just a massive cluster of LED on it. And if the group designing that product doesn't take thermal into perspective as they're doing the design, it certainly delays their release to market.
All right, Richard, in the market generally, are you seeing now that it's more important that heterogeneous integration is needed to really manage the transfer of heat through different devices?
It is, and I think it's as Chris said, it's down to not only the size of the components, but what they're doing with that as well. I mean, historically, you used to have a power board, and then there would be a power control board, and they weren't together; they were separate.
Yes.
Now, because of real estate, because they're trying to cram more and more functionality into areas of products that they didn't need to, now everything's on the same board. So you've got a board where one end there's massive heat generation going on, and the other end you've got all those little intricate control things that are making that power work properly, and that doesn't really go very well together. So that part of it is seeing more need for that heterogeneous processing, because you need to, when you're designing that board, you need to make sure you've got the heat capacity, the thermal capacity to take away the heat at the generation stage for those devices that are switching the power on and off, and the massive tracks that they have. So you need to have the board loaded up with quite large metal panels at that point to help transfer that, but transfer it to somewhere. And that's some of the issues that we see, is trying to get the heat out of the board into the coolant system or into the coolant fans. But also you're going to make sure that heat doesn't transfer down to those smaller, more delicate components. And that's where, again, you need to look at some of that heterogeneous types of products. So you're looking at like thermal pads or firmly conductive gap fillers or anything like that can help to dissipate the heat as quickly as possible. Not in massive like watts per meter Kelvin. Some of these things, if they're quite a large volume, you only need to have 1 or 2 watts per meter Kelvin to help spread the heat away. You don't want the heat build up in any one place. And that's kind of the issue that people have, is a lot of these large control components have thermal pads under them, and that helps to dissipate the heat away from the component. But then you've got to get it away from there, away from everywhere else, so you're not damaging the more delicate components around them.
Yeah. So what can the circuit material suppliers offer to help with this, Chris?
Yeah. Well, I can tell you what Ventec can to help, but Richard's explanation is spot on. And to be honest, if we go back 15, 20 years ago, the acronym IMS stands for insulated metal substrate. And historically, it was used as a single layer only type PCB. And as Richard mentioned, you had to use surface mount connection pins to attach a control circuit to it. The world has changed today. Nobody wants to have a 2-board system and rely on some surface mount pins to connect the two. So companies are coming to us saying, look, we want a board that dissipates heat on 60% of the board, and then I want my logic components on the other 40%. So it's forced Ventec to become quite creative in developing some thermal prepregs that can be used in what I would call a hybrid stack. And by hybrid stack, I mean taking sometimes signal integrity, sometimes FR4, and in strategic layers within a cross section of that stack, inserting a thermal prepreg to help dissipate the heat down to a neutral zone or to a heat sink or to a metal base plate. But the days of just getting by in my world with a single layer board just don't cut it anymore. As these modules reduce in size, they oftentimes have to increase in layered count. And I can't just go to a design house and say, hey, all I can offer you is a single layer, a metal-based product to dissipate heat. I have to go there and offer that with other solutions that involve multiple materials.
Yeah, it's definitely becoming a more and more challenging. Challenging. I was going to say problem, but maybe problem's the wrong word. But it definitely does.
It's an opportunity, Keith. It's a more challenging opportunity.
It's an opportunity for some and a challenge for others. Yeah, I know. One of my pet topics, I come from the X-ray business, as a lot of people well know. And one of the things that we always worry about or are always asked about is voiding. And when people are working out, calculating thermal paths, do they take voiding into consideration, or are you still finding that they assume everything is going to be a perfect interconnection, whether it's a silver epoxy or whether it's solder or it's filled via holes or whatever they're using to transfer the heat?
Who are you asking that of, Keith?
Well, I think we'll go with you first, Richard.
And I would answer yes and no. So
Oh, I'm glad I started with you.
voids essentially don't have to be an issue. It depends on how big they are and where they are. So I think it's what you really need to understand is where the hot spots are on the component or on the area that you want to dissipate the heat from. And then you need to make sure that the voids are not as low as possible, but are less of a distraction as possible in that area. So if you've got a very large area pad that you're trying to dissipate the heat through, up to 50% voids generally probably won't cause you much of an issue. But if you've got a very small hotspot within a control chip that is going to cause you an overheat situation or a power runoff, then yes, you need to make sure that you've got the best conductance possible within that area. And what you're seeing is the use of more, as you said, of those conductive adhesives, the high metal loading materials. They can give you good conductance of 20-30 watts per meter Kelvin. And they don't use the term voids, they use the term of porosity to show that there's some holes there. That's very well controlled, and the conductive pathway is normally very well controlled as well. So if they say it's 20 to 30 watts, it generally is. The solder tends to be 60 to 70 watts per meter Kelvin, so there's a double the amount of conductance of heat. And again, the void in there generally isn't a big issue unless you've got a very big void. If you've got the big void in the area you don't want it to be, that's where you have the issue. So that's where you need to design some of these things a little bit better. And I've seen some boards where now they don't solder the whole of that thermal pad. The heat transfer part on the PCB is a small circle where that hot spot is. And that's where you put the solder. And then the amount of voiding in that very small area, because of the volume, is inherently less, which then means you get a good transfer. So it's more looking at the design of the PCB, understanding the components, and looking at how you can integrate that forward thinking to try and reduce the potential risk of voids if they are there. But voids on their own don't necessarily need to be an issue, but different types of voids can indicate different things that could go wrong. So it's a whole world on its own of what we can talk about.
Yeah, so effectively we're taking design almost to another level where it's not even designed for thermal conductivity within a component, but it's designed for thermal conductivity within an area within a component. Exactly. And then maybe specifying what's acceptable and what's not on a drawing just for that area.
Exactly. And certainly for things like the LEDs and for some of the high power processors, that's the way you have to go. You don't want to have a massive pad that could have something on it. You want to know where that heat is going to be biggest and then draw the heat away at that point with the best products that you can.
So you talked about the differences with thermally conductives and solder. It sounds like solder is still the best solution if you can get something that's fairly low voiding.
Exactly, and that's because it's a solid lump of metal. So even like the best conductive adhesives are just bits of metal holding hands. It's not integrated together. It isn't a metal to metal joint. It's touching. It's only where it touches is where you get the transfer. So solder's always going to be a little bit better. You know, sintering is going to be a step up as well, but it's a more complex process. But if it's something that you can use, then the sintering system probably is going to be the easiest handling way, and going forward probably the better way for a lot of people to look for some of these super high power processes that they're going to have to introduce as maybe electric vehicles become more powerful, and certainly the batteries within them become more powerful and longer lasting.
Okay, I've got a two-part question before Chris goes to sleep. The first one, sintering, if I remember correctly, involves higher temperatures than traditional soldering?
Yes and no. Depends on the technology. Some people are developing low temperature sinters, which can work at 180 to 210, so possibly slightly lower than the standard solders, and they can then withstand temperatures in excess of 500 degrees C. So there's a good compromise there. Problem with them is that it takes a different type of process to run, and they're not a drop-in thing. You need to have the right equipment, and you need to know what you're doing.
Yeah, and the second part of the question was, as we're talking about soldering, low temperature solders are getting a huge amount of press at the moment for all sorts of reasons. Would they be a reliable enough thing to put into an application like this?
It depends on how hot it's going to get. If you're looking at temperatures in excess of 100 degrees C, then again, you've got to be quite careful on what you think of as a low temperature solder. I'm starting to describe them as anything that solders less than 200 degrees C. So if you're using the traditional ultra low melting point solders that melt around 138 degrees C, you don't want to be exposing those temperatures much in excess of 105, 110, because they're going to start to lose some of their integrity. And if there's any stress involved, you may have some issues. If you're looking at the ones that are in 160, 170, 180 degrees C, you're probably going to be all right with temperatures around about 140, 150 degrees C for heat transfer. And that's pretty much all you really need to do for a lot of these processes. So I do see that as an opportunity, yes.
And what can you see from the materials point of view where you can generally add more help to this cause, Chris?
Great question. And the one thing I see in my space is the significant solder joint stress in certain applications. If you look at a cross section of it, we'll just call it a single layer IMS board, you've got a layer of aluminum, and then you have the Ventec dielectric, and then you have copper foil, and then you have solder, and then in the world of LED, the high lumen output LED, you've got a big ceramic chip on that copper pad. Each one of those components have wildly different CTE, or coefficient of thermal expansion, values. So it's any void in a solder pad schematic can initiate some additional stress, which eventually becomes a crack. And a crack is obviously a big no-no in the world of power, onboard charging, and LED. So the focus has come back to us in the IMS industry to develop dielectrics that are more compatible with the CTE of copper. In addition, we've had to research some alternative base plate materials. Traditional IMS, most designers like to use aluminum. It's less expensive than copper. It's pretty robust. It doesn't not often need to be plated or covered, and it's much lighter. So as we move into this world of hybrids and EV vehicles, weight of a design or board is outrageously important. So it's forced us, Ventec, to look at alternative dielectrics that are much lower modulus, that mate better with a solder that Richard is proposing to customers, so that they can thermal cycle the tar out of these products, and they don't see the strain on the solder joint.
And what challenges do you see
question.
going forwards, Richard?
You know what, I would agree with Chris. I think what we need to be doing more of is actually looking at all of the things that are on the board and what the board is itself. If we can, at that early stage, if we can all get together and agree on what direction we're going in and how we're going to do it, the actual design and the practicalities then of making it work become a little bit easier. So the earlier you can get people together talking about what thermal issues you might see, how we can overcome them, what the board technology is, what the solder tech is, what you have in the way of conductive materials you're adding on top of that, or devices you're adding on top of that to draw the heat away in the way of fans and stuff. The more integration we have talking about that sort of thing, the better the likelihood is the outcome at the end of it's going to be good. And that's, I think, the next stage that people designing these things need to start to actually look at, is not approach each thing separately. So not go to Chris and say, hi, I want a board that does this, and then come to someone like us and say, we want some consumable products that have these properties and can do this. Because we're going to compromise and Chris is going to compromise.
Exactly.
But if we know which direction we need to compromise, if we can compromise in the same direction and we can come up with a solution that works with what they want and give them what they want better.
Okay. Before I get to my favorite question, I'd just like to remind the audience that there's a Q&A box at the bottom. They're welcome to type in any questions that they may have, and we'll deal with them in a Q&A at the end. Right. Keith's favorite question for things like this. How do we get designers, board makers, assemblers, and testers to work more closely together?
Tell them how much it's going to cost if they don't.
Yeah.
Yeah, I mean, things that Chris's team have done with the design guide for boards is a help. But I've all my life, depending on who I've worked for, I've always struggled to be able to get that if you like the chain working, so that the guys at the beginning go all the way through to the end. I mean, I had a one, again showing my age, I saw one of the first BGAs in the States a lot of years ago, and it came from one of the big global manufacturers who did a presentation on how great it was and how much space it saved and everything else. And I simply asked him, how do you put it onto the board? And he said, pardon? And this was in the very, very early days of, surface mount was new. And we had this thing with 256 balls on the bottom. So that kind of brought home to me that there's a little bit of a gap where everybody's focused on doing their bit and they don't really think about the bits that go afterwards. I mean, as an industry, we need to be doing this a lot more anyway, because it improves yields, it reduces costs, it does all sorts of stuff. But especially where we've got thermal challenges, it becomes, if anything, more important.
Very true. You guys are both spot on. It's a function of getting the right people at the table during the design cycle. In my case, we make Ventec printed circuit board laminate. That laminate goes to a board shop. The board shop makes the board that oftentimes goes to a contract manufacturer. And then the finished product gets to sometimes a different assembler, and then on to the OEM. There can be 5 parties involved, at least 3 or 4. And it's certainly, it's not speed to market and it's not cost effective if all of those groups aren't speaking all the way through the process. For those OEMs that are vertically integrated and take a design to finished product, which that's not so common these days, they seem to, those designs, for me anyway, in my experience, have run smoother, and it's primarily because of communication.
Yeah. Anything to add, Richard? We've lost your sound.
Yeah, I know. I was just saying that to myself as well. I think Chris is absolutely right. I mean, that is the biggest problem we have, is that you're given a task to solve an issue, and then you give that to them, and it's kind of like you've thrown it over the fence, because you never hear back. You never get that feedback to say, well, very rarely, to say that, yeah, that worked, or no, it didn't. and oh yeah, can we speak to this guy who's the next person down the line so you can explain why you've offered that, or can you talk to this guy who's further before you to see what his issues are so that you can then tailor make your solution to what he's got. I mean, that's what we need more of. We need to be doing that to ensure that what we get isn't like I'm going to use the word a lucky mix to come up with something that works, and come up with something that's more focused on what the customer needs, what they actually need, what they can afford, and what will make it work.
Perfect.
Well said.
Yeah, right. Before we get on to the Q&A session, and audience, please remember it's the box at the bottom. Please type it in and we'll get to you after we finish this. Are there any points that you guys would like to share with the audience that we haven't really covered well in this discussion because I didn't do my job properly?
I think you've done your job properly, Keith. All I'm going to say is that, that don't be afraid to ask. Don't be afraid to, if you've got something and you're not sure what it is, ask. It's unlikely that it's going to be something that hasn't been seen before. And if it is something that hasn't been seen before, well done, because then the person you're asking is going to be really interested in it and will want to help. So, I mean, that's the key thing. Ask the questions and be quite pushy in what you're asking for so that you can get answers back that make sense and will work for what you want.
Chris?
100% agree. When I look to the 3 of the last 4 products we've released to market, really started with a discussion from a design engineer that was boxed into a corner and couldn't come up with a design scheme or product to work in their module. And the solder joint fatigue or stress dielectric we designed is a perfect example. We may not have gone down that path because I'll say this, people like me in the thermal industry, sometimes you get blinders on your head and all you keep thinking of is the next generation of product with higher thermal conductivity. And Richard touched on that earlier. It isn't always the highest thermal conductivity that's the key product characteristic for a designer. Oftentimes it's something else. It's electrical breakdown, or it's peel strength, or it's, in the case of solder joint stress, it's a low modulus product. So I 100% agree with Richard. I encourage anybody to reach out there. The old adage that there is no stupid question. There really isn't. When the traditional printed circuit board industry has kind of always just started with an FR4, low TG FR4 product. If that works, great. If it doesn't, then where do we go? And it's at that time when designers say to themselves, where do we go? I would welcome an email, a call, a text, just to say, hey, this is the challenge we're facing, because it's forced all of us in the printed circuit board world to really review our product line and become much more creative and flexible.
Yep, I think that's really good from both of you, and some really good answers, some really good discussion today. I have well, it's not actually a question, it's a comment here from Jim. And basically, he's been doing what we've been talking about since 1992. In other words, balancing the design to optimize the design features to meet the product requirements at the lowest risk, cost and size, etc., etc. But as he says, it's not always properly recognized, and unfortunately, until there's a quality failure or an expensive recall, and then everybody is excited about it. But yeah, it's good to know that at least in some areas of the electronics, and I have to say, given the companies he was working for that included Raytheon and Hughes and Delco, then he was working with at least some of the forward-thinking ones even then. So yeah, that's good.
I very much agree.
Yeah. So thank you for that, Jim. And we don't have any other questions, which either means we were very good or very bad. And as I've enjoyed today, I'm going to go for the fact that we were very good. I'd like to thank Richard from Harima.
Correct. Well done.
Oh, yeah. We got used to multi-core and then Henkel and now another one, but we'll get there in the end. And Chris from Ventec, I'm sure their email addresses will be available with the stuff that goes out afterwards. So if you have any direct questions for them or for me, and you're either too nervous, but as Chris said, there's no such thing as a bad question, only bad answers. So please get in touch with them. And I'd just like to thank you very much for listening today. I hope you've enjoyed it. I hope you've learned something, and hope you enjoy the rest of your day. So thank you, Richard. Thank you, Chris. Thank you
very much
for holding this whole thing together for us. And that's it from me.
Co-Young is leading a smart revolution that will change the world of electronics manufacturing. Based on our pioneering True 3D measurement-based inspection technology, we revolutionize the solder paste inspection market to such great lengths that 1 in 2 SPIs sold today is from Co-Young. Building our SPI technology, we expanded to automated optical inspection, also known as AOI. Every year, we introduce new award-winning innovations and have proudly earned the respect from thousands of customers across diverse industries. Aside from our R&D center in Korea, we have research facilities focused on artificial intelligence and deep learning across the world to help us further develop proprietary AI technologies for your challenges. With our global network of sales and service centers, we aim to respond quickly to your needs and to deliver the highest level of customer satisfaction.
Global SMT and Packaging opens the windows of the world to bring you the latest news and technologies from Munich, from Bangalore, from Shanghai, from San Diego.